Hey folks, here's your next video lecture, this one on Coulomb's law. Most of the important work that we're going to be looking at in this unit was laid out originally by the man you see on the screen there, a Frenchman named Charles Augustin de Coulomb. Coulomb was a pretty awesome guy. Like a lot of intelligent people of his period, he not only was gifted in the area of his major profession, but also had a wide variety of other interests. So Coulomb was a military engineer, he was a politician, and he was a scientist. A particular interest to him as a scientist was electric charge. What he was interested in is the mathematical relationship between the strength of the electric field given off by a particle and how that's related to the charges on the particles. So, charged particles exert forces on each other. We saw this when we played with a Van de Graaff generator today. You touch a Van de Graaff generator, a person's hair becomes charged, and it exerts forces on the other hair around it, which causes a person's hair to stand on end. So let's think again about what a force is. What does that represent? It represents a push or a pull on an object. As a result of his research, which I'm not going to go into too much detail here, is that the electric force proportional to objects is proportional to their charges. So, in other words, if you doubled the magnitude of one charge, you would double the strength of electrical attraction or electrical repulsion between the charges. In addition, the inverse square law applies in terms of the strength of the electric force and the distance between the particles. We saw this exact same mathematical relationship in Newton's law of universal gravitation. So here's the formula. The electric force between two charged particles is a product of something called Coulomb's constant, the magnitude of the charge on two particles, Q1 and Q2, divided by the square of the distance between them. If you notice, this formula is very similar to the formula for Newton's law of universal gravitation. In fact, there are some theories to suggest that there is some overall underlying property of the universe that generates both the electric force and gravitational forces, and therefore causes the mathematical computation of these forces to be very similar. Just like with gravity, the forces that attract or repel two charged particles act in a straight line between the molecules, towards the center of each molecule. In addition, the magnitude of the forces between the charges is equal. Again, another thing that we see here that works just like gravity. So just as you have the same gravitational attraction to Earth that Earth has to you, so too do two charged particles repel each other or attract each other with the same amount of electric force. One of the conventions of talking about the electric force is that we're going to write the electric force as a positive number, even if we end up with the attraction of a positive and negative charge, which would normally mathematically give us a negative number. What instead we're going to do, rather than leave the answer as a negative number, is write whether the force is attractive or repulsive. If we would normally end up with a negative answer, that means we have two opposite charges and they're going to attract each other. If we end up with two positive charges or two negative charges, they're going to repel each other. We're going to end up with an answer that's going to be mathematically positive. So let's think about how we can use this formula to solve problems relating to the forces on objects. So we have a proton and an electron that are 2 meters apart. What is the magnitude of the force between them, and is it attractive or repulsive? Solve this problem and then move on. So when we enter our values, we get an overall electric force of 5.76 times 10 to the negative 29th newtons, attractive. We should have been able to know this even before we did any math, because we're dealing with a proton and an electron. The force between a proton and an electron is one of the things that keeps electrons spinning around the nuclei of atoms. So here's a couple more problems. In question 1, I want to know what the attractive force is between a proton and an electron across the diameter of a typical atom. A typical atom has a diameter of about 5 times 10 to the negative 11th meters. For number 2, I want to know the repulsive force between two electrons. Well, actually, I give you that force. Let's see if you could figure out the R for me, how far apart they are. Work these two problems, and then move on. For problem number 1, it's a fairly simple matter of multiplying the charge of each particle by Coulomb's constant and then dividing by the square of the distance between them. Second problem is a little bit more involved. Here what I did is I multiplied both sides of my equation by r squared, then divided both sides by the electric force and took the square root of that answer, obtaining a result of 3.4 times 10 to the negative 10th meters. Pretty much all of the problems are set up just like this, and if you could do problems involving Newton's law of universal gravitation, you should do pretty well here.